Hi, folks. In this next section, we're going to learn yet another form of equation for quadratics and how to graph using that form. So here we are looking at intercept form, and intercept form looks like this. F of x equals a, some constant, times x minus p, some constant, times x minus q, another constant. And this is really just a polynomial written in factored form, which hopefully you remember from chapter 7. And so we're going to learn how this factored form can be useful when trying to graph quadratics. So let's look at an example here and how to graph a parabola using this format. F of x equals negative x plus 1 times x minus 5. Notice that our a value out front is -1. And just as we've seen in the previous sections, this is going to cause a reflection over the x-axis. It's going to cause a downward opening parabola, a sad parabola. But let's look at what happens here with having the x terms factored like this. What we see is that we are going to have x-intercepts at x equals -1 and at x equals 5. How do I know that? Because x-intercepts occur when y equals 0. And if I set my y, or my f of x, equal to 0, I end up with this multiplication problem. And just as we discussed in the previous chapter, if you have a multiplication problem equal to 0, then you know that one of the components of the multiplication problem must be equal to 0. It's the zero product property. So either, in this example, x plus 1 equals 0, and over here we have 0 equals x minus 5. So for the first equation, if we subtract 1 from both sides of the equation, we get that x equals -1. And for this second equation, if we add 5 to both sides of the equation, we get that x equals 5. So we see those values do come straight out of the factored form. You just need to watch the sign. So the signs in the factored form, generic form of the equation, tell us that there needs to be, if there's a negative sign there, then our intercept is positive value of x. If there's a positive sign there, our x-intercept is a negative value. So we have identified the x-intercepts, and we can plot those on our coordinate plane here. X equals -1 and x equals +5. But this doesn't help me graph the rest of the parabola. I need to know some more points here. And one of those the most obvious point to try to plot is the vertex. The vertex is like the most important point on the parabola. So how do I know where that vertex is going to be? Well, the fact that I've got two x-intercepts here lets me know where my axis of symmetry is. My axis of symmetry is going to be exactly halfway between those 2 points. So in this case, my axis of symmetry is going to be halfway between those 2 points. So in this case, I can do it by eye or just by counting and finding that halfway point. But a good general rule that always works, even when the numbers are awkward, is to just take an average of your two intercepts. So that would be -1 plus 5, adding those together and dividing by 2 because there are two numbers that I'm trying to average. So -1 plus 5 is +4 divided by 2. My axis of symmetry is going to be when x equals 2. So that is where I drew my blue dotted line here, but we can see where this value comes from. It's averaging the values for the two x-intercepts. I know where my axis of symmetry is, but I want to know where the vertex is. So I'm going to take that input value of 2, and I'm going to go ahead and plug that value into my intercept form of the equation to solve for y, to find out what the y coordinate is here. 2 plus 1 is 3, and 2 minus 5 is negative 3. So if I've got negative times 3 times negative 3, that all works out to be positive 9. So this here is my y value. So my vertex is at 2, comma 9. So if I come up here, 2 comma 9, that is where my vertex should be. And you can plot additional points if needed to kind of draw a more smooth graph, but I'll go ahead and draw my parabola in like this. And this is a graph of f of x. Now, here I'm asked to graph the function, but also define the domain. Remember, domain is all x values, and asked to find the range. So what are my possible x values on this graph? Well, I can go to the left forever. I can go to the right forever on this graph. There's no restriction, so my domain is all real numbers. And my range, there is a restriction in how far up and down I can go on this graph. I can go down forever and ever and ever, but I can only go up as high as y equals 9. So y needs to be less than or equal to 9. Remember, the range is always going to be tied to the y coordinate on of the vertex. So you can use that number to help you describe the range. All right, let's look at another example. This example has not been pre-factored for us. We've learned how to factor quadratics back in chapter 7, and now we're expected to use that skill moving forward in this chapter. So, remember, when you are fully factoring a polynomial, the first step is to look for a greatest common factor. So 2 and 8 share a greatest common factor of 2. So I'm going to rewrite f of x as being 2 times x squared minus 4. And when I look at that polynomial, I see a special pattern. I see a special pattern because my first term here is a squared term, and my c term is a squared term, and I am subtracting those two values. This follows the pattern of 2 times x plus 2 times x minus 2. That first 2 I just copied down from the previous version of the equation. That just went straight down there. But the rest of this came from that quantity in parentheses. I spotted a special pattern and could factor it out this way. Now, if you don't recognize the special pattern, you might need to look at this as being x squared plus 0x minus 4. And you're thinking about the factors of negative 4 that add up to 0. And if you think about the factors of negative 4 that add up to 0, that would be positive 2 times negative 2. And so that's where the positive 2 and the negative 2 come from. All right, now that I've written this in factored form, I can follow the procedure that I did above to graph the parabola. According to this factor here, my x equals negative 2. So I'm going to have a x-intercept at y equals negative 2. And from this one, I'm going to have x equals positive 2. So I'll have another root, another x-intercept over here. And because my intercepts are at -2 and +2, if I take the averages of those, -2 plus 2 is 0, and 0 divided by 2 is 0. So my axis of symmetry is right here on the y-axis. And if I go ahead and plug in that x value of 0, this is my axis of symmetry. If I plug in that 0 value into 2 times 0 plus 2 times 0 minus 2, that works out to be 2 times +2 times -2, and that works out to be -8. So my vertex is at 0, comma, -8. So I want to have a point down here, and I'll draw my parabola like this. And I have graphed the function 2x squared minus 8. I haven't yet found the domain and the range. So the domain in this case, as with all parabolas, or at least all parabolas that don't come from a story problem. If you had a real world scenario, it might not be a domain of all real numbers, but mathematically, parabolas can encompass all x values. The range, as before, is going to be tied to the y coordinate of the vertex. And so here the range can be any y value that is greater than or equal to -8. When you're finding zeros of a function, functions have zeros, graphs have x-intercepts. They are tightly related to each other. Technically, you use different vocabulary words, but I know I myself am guilty of using the two interchangeably. If I want to find the zero of a function, first you need to have a fully factored polynomial. And then, just as we did in the previous example, you need to say that the y value, the f of x value, is 0. And then you use the zero product property to determine the x values to give you the x-intercepts, those zeros of the function. So here, using the zero product property tells us that if this multiplication problem equals 0, then either x minus 1 equals 0 or x plus 2 equals 0. If we add 1 to both sides of the equation, we get that x equals 1. And if we subtract 2 from both sides of the equation, we get x equals -2. And those are our zeros for this function. So the process is fairly straightforward if the function is pre-factored for us. What if we need to factor the function ourselves? In this example, for g of x, this is not a factored function. You cannot use the zero product property unless you have a multiplication problem. This right now, this polynomial is an addition-subtraction problem. So we need to factor this out into its as much as possible till it's fully factored. I'm going to factor out a -2. All of my values here, my a, b, and c terms are all negative, so I can factor out a negative number. And they're also all multiples of 2. You really want, when factoring, to try to remove the negative from the first term so that you can follow the strategies we learned in chapter 7. Chapter 7 for factoring. So I'm going to remove the -2. And now I'm left with x squared, because -2x squared divided by -2 is just x squared. Now I've got -10x divided by -2. A negative divided by a negative is a positive, and 10 divided by 2 is 5. So that's going to be 5x. And lastly, -12 divided by -2 is +6. This polynomial looks a little less scary. Remember, you should kind of multiply your A value times your C value, and then find factors of AC that add up to B. Factors of AC that sum to B. Well, A times C is 1 times 6, and that equals 6. And I want those factors to add up to 5. So what are some factors of 6 that add up to 5? 1 and 6 add up to 7, but 2 and 3 add up to 5. So those are the factors I wish to use, and I end up with x plus 2 times x plus 3 as my factors, but I also need to remember to have that negative 2 out front. I've now fully factored my function g of x, but I haven't actually answered the question yet. Remember, I want to find the roots of this function. I want to find the zeros of the function. So I need to set my function equal to 0 and then use the zero product property. One of the components of this multiplication problem must be equal to 0. So either negative 2 equals 0 or x plus 2 equals 0 or x plus 3 equals 0. Well, hopefully it's obvious that negative 2 does not equal 0. That does not help me get a 0 for the function. That's an untrue statement. But x plus 2 equals 0. If I subtract 2 from both sides, I get that x equals negative 2. And for x plus 3 equals 0, if I subtract 3 from both sides, I get that x equals negative 3. So my two zeros for this function are x equals negative 2 and x equals negative 3. Let's look at one more example here. This looks like it is a fully factored function, but it's not actually completely factored. When you have just x as in one of the factors, then it's fine. You can't factor that anymore, unless I suppose if there were a coefficient, a greatest common factor, you could perhaps factor something out. Here, though, with this x squared is a square value. Negative 16 is a square value. This is a difference of two squares special pattern. This is the same sort of special pattern we saw up here on the previous question, B. This was a difference of two squares pattern. So this can be factored reasonably straightforwardly, or you can factor it the old-fashioned way by thinking of this as being x squared plus 0x minus 16. But we're going to have x minus 4 times x plus 4 as our factors for this x squared minus 16 term. Okay, I now have a fully factored function. I need to set this equal to 0 if I want to find the roots of my function, the intercepts of the function. Notice this is not a quadratic function anymore. This is actually it's called a cubic function because I'm going to end up multiplying x times x times x. So I'm going to get an x cubed term here. But the process is still the same. This is a polynomial. I've written it in factored form. And so this time I'm just going to have 3 possible zeros instead of 2. That's the only difference. So either x minus 1 equals 0, or x minus 4 equals 0, or x plus 4 equals 0. If I add 1 to both sides of the equation, I get x equals 1. If I add 4 to both sides of the equation, I get x equals 4. And if I subtract 4 from both sides of the equation, I get that x equals negative 4. So those are my 3 possible zeros for this function. using zeros to graph a quadratic function. This is really what we've been doing so far. We're just putting all the steps together. We need to write the polynomial in intercept form. Then we need to find and plot the zeros. And then we follow the graphing steps that we learned in part A. So x squared minus 2x minus 3. I want to find the factors of AC, which is 1 times negative 3, so negative 3. Factors of negative 3 that sum to negative 2. What are my factors of negative 3 that sum to negative 2? I want my bigger factor to have a negative sign so that when the only way to get a negative number is to multiply a negative number times a positive number. But I want to put the negative sign on the bigger number. Negative 3 times positive 1, that sums to negative 2. So my factors here are going to be x minus 3 times x plus 1 equals h of x. This is the factored form of the polynomial. I want to use the zeros to help me graph. I want to use those x-intercepts to help me graph the parabola. So I'm going to set my polynomial equal to 0, and that's going to help me find the zeros. Either x minus 3 equals 0 or x plus 1 equals 0. So either x equals positive 3 or x equals negative 1. And so I'll go ahead and plot those zeros, either x equals negative 1 or x equals positive 3. Take the average of negative 1 and positive 3 so that you know the axis of symmetry is right here at x equals 1. So I need to find the y-coordinate for my vertex. So I'm going to take that input value of x equals 1 and plug it into my original equation to find out that, let's see, 1 minus 2 minus 3 is negative 4. So my vertex is at 1 comma negative 4. 1 comma negative 4. There's my vertex. And so I can draw a parabola through the points that I have highlighted, and I'll try to draw a reasonably smooth one. And this is using zeros to graph to graph a parabola. So we have learned lots of different strategies for graphing parabolas. How about going backwards? What if I kind of know what the parabola looks like and I'm trying to write the equation? Or I'm given certain features of a parabola and I want to write the equation. I can use different strategies. I can use different formulas that we've learned depending on what information I'm given. For instance, if I know the vertex of my parabola, then I can use the vertex form of the equation to help me write the correct formula. If I know my vertex is at negative 3 comma 4, well, the vertex is at h comma k, so I want to kind of plug things in. I'll just write the generic formula first. Okay, and I want to put negative 3 in where the h is, and I want to put 4 in where the k is. So that's going to look like x minus negative 3 squared plus 4. I need to simplify this a little bit because I shouldn't have two negatives next to each other. I want to have a times x plus 3, the quantity squared, plus 4. Now, for this example, if you remember from last class, if I want to actually figure out what my a value is, I need to know more than just the vertex. I need to know how stretched out the points are or how shrunk down the points are. In this example, I wasn't given another point on the parabola. Therefore, I just get to pick any value of a that I want. And the value of a that I want to choose is the simplest one, just the value 1, where I can just decide that my final function is x plus 3, the quantity squared, plus 4. That was my choice. You could have chosen to use the value 2 or negative 37, whatever value you wanted, because the only restriction I was given here was the vertex. If I was given a different point on the graph, I would have been able to plug that in, which you will see here as we move on and get to part 3. In this next example, I'm supposed to write a quadratic function. Oh, I'm sorry. I'm supposed to write this in standard form. I didn't follow my own instructions, so I'm not finished with this yet. I need to write this in standard form. So I need to multiply out my x plus 3 times x plus 3. Might help to write it out in fully kind of displayed form instead of the squared form, plus 4. So that then I can focus on using FOIL if necessary to multiply this together. So x times x is x squared. X times 3 is 3x. 3 times x is 3x. And 3 times 3 is 9. And we're going to combine like terms wherever we can, and we end up with x squared plus 6x plus 13. Okay. I suppose I should write, y equals or f of x equals. Let's move on to the next example. In the next example, I know the zeros. If I know the zeros, then writing an equation in intercept form as my first step is the best strategy. So if my zeros are at -5 and +4, that means that the factors, if you think of this as being my p value and this as being my q value, then I have x minus -5 times x minus 4. Again, simplifying this, I shouldn't have two negative signs next to each other. I've got x plus 5 times x minus 4. Remember, there are negative signs built into this equation so that you can plug the values, the zeros, as they are given to you. Once again, this equation should have a multiplication factor out front. I was not given any more information about this graph other than the zeros. So I have no way of knowing, let's see, my zeros are at -5 and +4. I have no way of knowing if my graph goes this way or if it goes this way or if it's really stretched out with a vertical stretch. I'm not given enough information to tell that. So again, I'm kind of left to my own devices to make this as simple as possible. I'm going to choose an a value of 1. So I'll just call this x plus 5 times x minus 4. If I'm going to write this in standard form, I need to distribute. I can't leave it in factored form. So x times x is x squared. X times -4 is -4x. Positive 5 times x is 5x, and 5 times -4 is -20. So that all works out to be, let's see, f of x equals x squared plus x minus 20. Okay. Now, I've hinted at this earlier that there is a way to solve for a, but you need a little bit more information. You need an additional point that isn't the vertex if you're doing vertex form, or that isn't the zeros if you're doing intercept form. And question C here gives us that kind of example. We're told that this parabola passes through -9, 0, -2, 0, and -4, 20. In this, for this parabola, we know two x-intercepts. These are my x-intercepts here and here, and I know that they're my x-intercepts because y equals 0. Because I know the zeros, going with intercept form makes the most sense. And so if I do f of x equals a times x minus p times x minus q, -9 can be my p-value, so I'll do a times x minus -9. And -2 can be my q-value, so I'll do x minus -2. And I end up with, when I kind of simplify those double negatives, I have x plus 9 times x plus 2. Now, for the previous examples, I said, I can make up whatever value I want to for a because I don't have enough information about the parabola. Now, I do have more information about the parabola. I know that I want this to be one of the data points, one of the input-output pairs in my parabola. So -4 is going to be my x value, and 20 is going to be my y value. So I'm going to plug in those values for x and y. X is -4, and y is 20. So this will be 20, and I needed to have another -4 over here. And the rest of the equation is going to be the same. I still have an a value here. I still have to add 9 here, and I still have to add 2 here. So this now, the only unknown variable in this equation is the a value. -4 plus 9 is +5, and -4 plus 2 is -2. So I'm going to have a times 5 times -2 equals 20. And if I just kind of bring the problem up here again, simplifying this a bit more, 20 equals a times 5 times -2 is just -10. So to get a all by itself, to solve for a, I need to divide both sides by -10, and I get that a equals -2. I can plug -2 into my the version of the equation that I had at kind of almost the first step here. I'm going to plug -2 into there, and that's going to give me f of x equals -2 times x plus 9 times x plus 2. I suppose it was actually this version of the equation that I used. This is a complete equation, although the instructions did ask me to give the equation in standard form. So I should kind of do the distributive property to multiply my factors together. I'm going to have -2 out front. X times x is x squared. X times 2 is 2x. X times 9 is 9x. And 9 times 2 is 18. And kind of combining like terms here, I get -2 times x squared plus 11x plus 18. And the last thing I need to do is just kind of distribute that -2 through the onto each term in the polynomial. And our final answer, let me write it up here in a different color so it stands out a bit more. Our final answer is f of x equals -2x squared minus 22x minus 36. So the real trick here is using your extra point, your extra piece of information. So if you've got it in vertex form, you need a point that isn't the vertex. If you're doing zero or intercept form, you need a point that isn't one of the zeros. In order, you kind of need an asymmetric point to solve for A, to get an x and y value to plug in to your almost complete equation so that you can rearrange and solve for A. I kind of hinted at this earlier, but this strategy that we're learning works for more than just quadratic equations. It works for more than just parabola-shaped graphs. It works for cubic functions as well. So here we're told to use zeros to graph this cubic function. We want to factor this polynomial the same way that we learned to factor polynomials back in chapter 7. We start by factoring out any greatest common factors, if there are any, and x cubed and negative 4x both share an x term. So I'm going to factor that out. X cubed divided by the x that I'm pulling out is x squared, and negative 4x divided by x is just negative 4. And now I see, and we've seen this once already today, this is the difference of two squares pattern. So this factors further into x minus 2 times x plus 2. This initial x term is just still there from above, but I've taken the x squared minus 4 term and further factored that into x minus 2 times x plus 2. I can now find 3 zeros to graph here. Either, I'm just going to set this whole thing equal to 0. Either x equals 0, or x minus 2 equals 0, or x plus 2 equals 0. So this first equation is already solved, x equals 0. I can add 2 to both sides of the equation and get that x equals plus 2. Or I can subtract 2 from both sides of the equation and I get that x equals negative 2. So I have a 0 here, and I have a 0 here, and I have a 0 here. In order to actually be able to graph this, I need to know what's happening between those zeros. And so much like we did for parabolas, I'm just going to make a table of input-output values where I test some of those numbers that are between the zeros that I know about. So I know that there's a 0 at 0. I know that there's a 0 at negative 2. I know that there's a 0 at positive 2. So I'm going to test some values kind of in between here. I'm going to test, I don't know, negative 1 and positive 1. I'm going to test negative 3 and positive 3. And I'm going to get some values in between these and outside of these zeros so that I know what the rest of the graph looks like. If I input negative 3 into the equation, I get negative 15. If I input negative 1 into the equation, I get positive 3. If I input positive 1 into the equation, I get negative 3. And if I input positive 3 into the equation, I get positive 15. So I can't graph that far down. I've got a point way down here and way up here for positive 3. But I can graph this value and this value. So I have some sort of curvy shape. This is typical of a cubic function that looks kind of like this, that I use the zeros to graph and then tested a couple numbers between the zeros so that I could see whether the function was increasing or decreasing between those zeros. This graph here represents a cubic function. Write the function in standard form. Just like we did with the parabolas, we can use intercept form. It's just that when you have a cubic function, you can have up to 3 zeros in your graph. So I can write this cubic function, x minus p times x minus q times x minus r. Here are my 3 zeros. So I have an a value that I don't know what it is yet, but I've got x minus 0. I'm going to call this one for my p. I've got x minus 2. I'll call this one my q. And I've got x minus 5. I'll call this one my r. And now I can work backwards, just as I did with the quadratic examples. I can figure out what A is because I have one other point that isn't a 0 that I can use to plug in x and y values in this equation. So this is going to be my x value, this is going to be my y value, and I'll plug those values in. 12 equals, let's see, x is 3, x is 3, x is 3. So I plug in x everywhere I see the number 3. I plug in the number 3 everywhere I see x. And the rest of this function is just the same. I have to subtract 0 here, subtract 2 here, and subtract 5 here. To solve for a, I need to kind of simplify each part of the problem. So I've got 12 equals a times 3 minus 0 is just 3. 3 minus 2 is just 1. 3 minus 5 is negative 2. So if I multiply together all the numbers I have on the right-hand side here, I've got negative 6 times a equals 12. So I divide both sides by negative 6, and I get that a equals negative 2. So I'm going to take this version of the equation and plug a equals negative 2 into that version of the equation, and I get f of x equals negative 2 times x minus 0 times x minus 2 times x minus 5. We need to write this in standard form, but there's a bit of simplification that we can do here first. First of all, I don't need to write anything minus 0. I can just kind of get rid of that minus 0. So we're going to have negative 2 times x times x minus 2, the quantity, times x minus 5, the quantity. So I'm going to rewrite this with the negative 2x out front, and I'm going to use FOIL to multiply those two polynomials together. So x times x is x squared. X times negative 5 is negative 5x. X times negative 2 is negative 2x. And negative 2 times negative 5 is positive 10. I'm going to combine like terms to simplify this a little bit more. X squared minus 7x plus 10. And then I'm going to multiply by the negative 2x that I have outside parentheses. I'm going to distribute this to each term inside the parentheses. And that's going to give me negative 2x cubed. X times x squared is x cubed. Plus 14x squared minus negative 2 times 10 is negative 20, and bring the x over as well. So my final polynomial is negative 2x cubed plus 14x squared minus 20. So the rules that we've learned for graphing quadratics, graphing parabolas, also work for more complicated functions, such as cubic functions. I hope this helped.